Today we are going to discuss inter-symbol interference, or in the short form it is called ISI. Well, the absolute bandwidth of rectangular multi-level time-limited pulse is infinity. If these pulses are filtered improperly as they pass through a say communication system or channel, they will spread in time, and the pulse for each symbol may smeared into adjacent time slots and cause this type of inter-symbol interference. So let us see how it happens. A highly defined, say, rectangular pulse, while passing through the channel, may be smeared in this way. So it will spread in time. So if you consider a number of pulses, like say, just consider this situation. Say we have 1011. This is the data, and this data is passed through a long channel, and after having distortion, all the pulses will be smeared and spread in time. So what happens, this pulse will spread, also this pulse will also spread, so something like this. So effectively at the receiver it will receive a waveform like this, and when we will take the sample, it may happen that this voltage actually should be small voltage value because it is 0. It may have certain value at it may cross, because of this smearing or spreading of pulse, this particular sample may cross the threshold voltage, so the received signal will be 1111 instead of 1011. So this phenomena is the inter-symbol interference. That means because of the spreading of pulses, if we receive erroneous signal, then it is the ISI. That is the actual effect of ISI. Now let us try to resolve this difficulty by using pulses which are band limited. So they can be transmitted intact over a band limited channel, but band limited pulses cannot be time limited. So obviously various pulses will overlap, and that will cause ISI. Thus, whether we begin with time limited pulse or band limited pulse, it appears that ISI cannot be avoided. So it is actually inherent in the finite transmission bandwidth. Fortunately, there is an escape from this problem. Pulse amplitudes can be detected correctly despite pulse spreading if there is no ISI at the decision making instant. So that is the main logic behind this all discussion. This can be accomplished by a properly shaped band limited pulse. So Nyquist first discovered different methods for pulse shaping that could be used to eliminate ISI. Out of this, we will discuss just main portion of this discussion, what Nyquist has proposed. So we will discuss now the Nyquist criteria for 0 ISI. This is the also called the first criteria. Nyquist achieves 0 ISI by choosing a pulse shape that has a non-zero amplitude at its center, say at t equal to 0, and 0 amplitudes at other sampling instants. So we can define this pulse shape like this. Pt is the pulse shape is equal to 1 for t equal to 0 and 0 for t equal to plus minus n into tb. tb is the sampling instants, 1 by rb. rb is the bit rate. So what does it mean? It means that the pulse will be present at a particular sampling instant. For this pulse, sampling instant is say t equal to 0. But for other sampling instants, n may be 1, 2, 3, 4, etc. In other time, the pulse will be 0. Now, point is, this pulse shape is not telling us what is the condition of the pulse at other times. It is in other times, like if t is not equal to ntb, some other time, say n by 2 tb or n into 2.2 tb, something like that. So under those conditions, whatever may be the shape of the pulse, whatever the ISI may be there or may not be there, we are not bothered. We are not going to bother those things. But thing is that the criteria is such that at particular time, at one particular time, it will give you some value, and other sampling instants, it will not going to give you any signal. That is the only criteria. One pulse satisfies this criteria, this criteria, that is the sync pulse. So consider this sync pulse. We are all familiar with this pulse shape. This is 0, minus tb, minus 2 tb, etc. So as you can see, the sync pulse that can be written as, say, pt equal to sync pi rb t. It is 1 at time t equal to 0, and at time tb, twice tb, 3 tb, 4 tb, minus tb, etc. all these are the sampling instants, the value is 0. So it is satisfying this criteria. Now if we take its Fourier transform in its spectrum, it will be something like this, square. This is 0. This is PF. So its bandwidth is RB by 2 Hertz. And this rectangular pulse can be written as 1 by RB omega by 2 pi RB. So this pulse satisfies the Nyquist first criteria that we have already discussed. Though this pulse is satisfying this Nyquist criteria, but there is a problem with this pulse. First of all, these ripples actually extends to infinity. So it will start at minus infinity and it will end at plus infinity. That means this pulse is impractical. Not only that, amplitude of these ripples decay at a very slow rate, at a rate of say inverse of the time. So if there are any small shift in sampling time, the interference will take place as the pulse decays too slowly, and the interference of huge number of pulses will be there. So that's the problem. I mean that is another problem. So we have to determine a pulse shape. So this pulse cannot be realizable pulse. This is non-causal. So we have to determine a pulse shape that we can actually implement, and it should decay at a faster rate than 1 by t. But for that we have to make some compromise, and that compromise is the bandwidth. Here the bandwidth is the minimum. If RB is the bit rate, then bandwidth is RB by 2 Hz for this pulse. So this is the minimum bandwidth. So if we want to change the pulse shape, then we have to compromise the bandwidth, and we are allowing the bandwidth in between RB by 2 to RB. So we have to take care of this fact that though we are trying to design or reshape this pulse, the bandwidth should not be greater than RB, and this is the minimum bandwidth. So we are allowing some more bandwidth, but that we are restricting the bandwidth to not to go beyond this RB. So this is our criteria for the selection. So let us assume that PT is our pulse shape and its corresponding spectrum power spectral density is this. Now this pulse PT must satisfy this criteria that is implied. Now if we sample PT every TB seconds by multiplying PT by an impulse train written as delta TB, then because of the property, this one, all the samples except one at the origin are 0, right? So thus the sampled signal say P bar T can be written as Pt into delta TB T, that is equal to delta T. We know that the spectrum of sampled signal P bar T is the spectrum of Pt repeating periodically at intervals of the sampling frequency omega b. Omega b means omega b equal to 2 pi Rb. So therefore the Fourier transform of both sides of this equation leads to 1 by Tb n equal to minus infinity to plus infinity P omega minus n omega b, that is equal to 1. Or if we multiply both sides by Tb, we can get summation of n equal to minus infinity to plus infinity P omega minus n omega b equal to Tb. That means the sum of the spectra formed by repeating P omega, every omega b is constant Tb. So the new pulse shape that we are going to design may be like this. This one is omega b, we are plotting with respect to omega. this is omega b by 2, this is 0, minus omega b by 2 and minus omega b. So if this is the pulse shape, then the addition of all the pulses must be constant. So say this is one pulse, this is another pulse, again there will be some another pulse will be there. So this one is somewhere here, omega b by 2, omega b minus omega b by 2, and so on. So this criteria must be satisfied by this pulse. Now if you see this figure, you can see that this summation takes place over maximum of 2 pulses right here, otherwise there will be a single pulse. So we can write, considering this pulse shape, this criteria may be written as p omega plus p omega minus omega b equal to Tb for 0 to omega b. Now let us change this origin, because we are more interested right here how it falls. So we are going to change the origin. Putting omega equal to x plus omega b by 2, we can rewrite this equation as p of x plus omega b by 2 plus p x minus omega b by 2 equal to Tb for x less than omega b by 2. Or in other words, we can write p omega b by 2 plus x plus p star omega b by 2 minus x equal to Tb for the same condition. P star means complex conjugate. Now if we assume p omega can be written as the magnitude part along with some phase part, then this term, exponential term, represents the pulse time delay. It is a time delay, and this section needs to satisfy this equation. As also this p omega is real, this portion, it implies that p omega b by 2 plus x magnitude plus magnitude of p omega b by 2 minus x, that is equal to Tb for x less than equal to omega b by 2. So p omega has an odd symmetry about the set of axes intersecting at point x. Also, you must have seen that p of omega b by 2 is 0.5 of p0. Now in this case, this p omega should have a bandwidth of p omega. It is slightly greater than omega b by 2 but less than omega b. So we are considering it as this excess portion is the omega x. That means omega x is the bandwidth in excess of the theoretical minimum bandwidth. Let us introduce a parameter called R equal to excess bandwidth divided by theoretical minimum bandwidth. So excess bandwidth is omega x, theoretical minimum bandwidth is omega b by 2, that is twice omega x by omega b. Now we have also already mentioned that maximum value of omega x max is omega b by 2. So range of R is in between 0 to 1. That means when omega x equal to 0, R will be 0 and so on. And when omega x equal to omega b by 2, R equal to 1. So the instead of considering this circular frequency, if we come to the linear frequency range in hertz, so theoretical minimum bandwidth, it is RB by 2 hertz. Excess bandwidth, say fx, is R into RB by 2 hertz. So the bandwidth of pulse, say Bt, equal to addition of these two, RB by 2 plus R into RB by 2 equal to 1 plus R by 2 into RB. This R is the roll-off factor. So this R actually determines how fast the pulse will fall to 0. One family of pulses that satisfies this Nyquist criteria, that can be written as P omega equal to half of 1 minus sine pi omega minus omega p by 2 and that divided by 2 omega x for omega minus omega b by 2 less than omega x. 0 for magnitude of omega greater than omega b by 2 plus omega x, and 1 for the reverse case. So if you plot this pulse, only the magnitude part, one-sided magnitude plot. This one is say omega b by 2, this is 1, and that is omega x equal to 0, means R equal to 0. Now if you change this R value, we will see the change in shape like this. Say omega x equal to say omega b by 4, that means R equal to 0.5, and This one is for omega x equal to omega b by 2, that means r equal to 1. This is omega b. If we plot in time domain, we can see it is a usual sync pulse. For r equal to 0, this is for r equal to 0, TB twice TB, etc., minus TB. And if you change it, say for r equal to 0.5, then it will be something like this. So its magnitude will be diminished. Something like this. This one is for r equal to 0.5, this dotted line. And this line for r equal to 1, it will be something like this. Something like this. So this one is for r equal to 1. For the case of maximum value of omega x, that means for r equal to 1, this equation may be written as 1 plus cos omega by twice rb, rectangular function of omega by 4 pi rb, that is equal to cos square omega by 4 rb, rectangular function omega by 4 pi rb. So this characteristics is called the raised cosine characteristics, because it represents a cosine raised by its peak amplitude. It is also called the full cosine roll-off characteristics. Now corresponding Pt can be written as Rb cos pi Rb t by 1 minus 4 Rb square t square sinc pi Rb t. So we can see the feature of this raised cosine pulse, that its bandwidth is omega b, or in terms of hertz we can call it as Rb hertz. Then it has 0 at other sampling instant. That means it is satisfying Nyquist first criteria. Not only that, the amplitude of these ripples are comparatively smaller. Sorry, this I have made a mistake. It will be like this. Yeah. This one is not this one. Actually, it crosses the zero in between two sampling instants, like this one. It crosses the zero twice. So this is one of the feature of this pulse. That means its amplitude diminishes at nearly 1 by t to the power 3. 1 by t to the power 3. So that means it decays at very fast rate. That means it is relatively insensitive to the variation of RB, sampling rate, timing jitter, something like that. And not only that, the basic criteria, the basic problem of that the sync pulse was it was not realizable, but this one is realizable because it has a finite uh, time. Means it is not infinite time duration pulse, it is a finite time duration pulse. So these are the properties of phase cosine pulse.